limits and continuity, and actually this is a topic that you have already become familiar with, whether you really realized it or not, just as we've been talking about limits. But basically, for a function f of x to be continuous at a point C, three things need to happen. First of all, f of c needs to be defined. So f of c is defined, meaning that there is a value at f of c. Hopefully this shows up all right. And secondly, the limit as x approaches c of f of x has to exist, right? So there has to be a limit and an actual value. And finally, the limit as x approaches c of f of x needs to actually equal f of c. So let's talk about that a little bit more. Sometimes we don't have discontinuity, and in that case we have discontinuity. Well, what kind of discontinuity can we have? First kind we're going to talk about is removable, point, whole discontinuity. These are all the exact same thing, and you've already seen this on some of your assignments, and some of you already talked about it. So removable discontinuity would be like if we had something like this, right? There's a hole right there. We do have a limit, but we don't have continuity. Or we could have something like this. Maybe you just have like that going on. Again, we have a limit, but we don't have continuity. And now in this type of a graph, we might even have an actual value here, right? So let's say this is our point C. We have f of c, and we have a limit as x approaches c, but our final condition, they are not equal to one another, so we don't have continuity. Another type of discontinuity we can talk about is jump discontinuity. And jump discontinuity is something you've also seen before. This is basically when we have a graph, maybe something like this. I don't know, like that, right? Or if you just had, I guess, a graph and it's going like this, and then from here up, whatever, something like that. There's a jump, there's a break in between what's happening. And finally, the last one we want to talk about is an infinite discontinuity, and you've seen these as well. This is when we have kind of our limits going to infinity. So if you have maybe like an asymptote here, right, you've got something going up like this and then something going down like that. There's an infinite discontinuity there. You do have a limit, actually a limit coming from the left and a limit coming from the right. You could even have, something like this if you just had like a, and then there's an asymptote here. You do actually have a limit, and the limit's the same coming from the left and the right in this situation, but you don't have a value at f of c, right? Here's c right here. So those are the kinds of discontinuity we talk about. But let's talk a little bit more about continuity. I'm actually going to pull up a paper here just because I think this is easier to see. And you'll see this, I'm going to upload it to our Google Classroom, but there's some definitions of continuity, some facts and theorems. So, first one, on an open interval. It's continuous on an open interval if it's continuous at each point on the interval. So, like here, if I was looking at this graph, it's not continuous on an open interval here because I have a discontinuity there, right? On a closed interval, it's continuous on a closed interval if it's continuous on the open interval and from the right at A and at B. So you don't have holes at the very ends there. Properties of continuity. You can multiply it by a scalar. It will still be continuous. Sum or difference of two continuous functions will still be continuous. The product of two continuous functions, still continuous. The quotient, if g of c is not equal to 0, they're still continuous. Compositions, they're still continuous. Basic stuff right there. Polynomials are continuous over real numbers. Rationals are continuous if q of c is not equal to 0. Your domain cannot be 0, or your denominator, excuse me. Y equals x to the 1 over n. If n is odd and continuous from 0 to infinity, it's continuous on all reals if n is odd, and continuous from 0 to infinity if n is even, right? So you can graph, try graphing x to the 1 over 2 and x to the 1 over 3, kind of see the difference of those. X or sine and cosine, those are continuous. B to the x is continuous when b is greater than 0 and does not equal 1. The log base b of x is continuous. Here, inverse function is continuous. One-sided. Left's continuous if the left hand is equal to f of x. right continuous if the right hand is equal to f of x. And actually, this should be a C right here. That should be a C. So make a note there in your own notes. Suppose f of x is defined in the open interval containing x equals c. Then f is continuous at x equals c if the limit as x approaches c of f of x is equal to f of c. This is actually what we already defined at the beginning of this lesson. So that should make good sense to you. So let's put some of this into practice. Tell me, is this continuous or not? Yes or no? Take a moment and think about that. Pause. Come up with your answer. If you said no, you are correct. It's a jump discontinuity, but let's actually prove that. So let's use those 3 steps that we talked about. So first, f of 1, that's where, I'm sorry, did I say that? I want to do this. Continuous or not at, oops, that should be a t, at x equals 1. That's what we want to talk about. At f of 1 there, x is actually equal to 1, 2, 3. 3. Clearly I didn't have my graphs very well labeled before I recorded this, but we can all suffer. All right, 2. Do we have a limit? The limit as x approaches 1 from the left of f of x, well, that's equal to 1. Pointless. The limit as x approaches 1 from the right of f of x, that's equal to 3. Well, then we already know that our limit does not exist, right? The limit as x approaches 1 of f of x does not exist. I should put an equal sign right there. And then finally, f of x, or f of 1, is not equal to the limit as x approaches 1 of f of x. Therefore, we don't have continuity. All right, let's do our second one here. Actually, I might just skip that one because I think you're kind of going to get the idea. Let's do our third one. Do we have continuity there? Well, go ahead and think about it for a second. Did you say yes? You are correct. We do have continuity there. So even though we have a cusp, we actually do have continuity. Let's prove that. So for point 1, f of 1 is equal to, let's call it 2. Again, I didn't label my graphs very well. The limit as x approaches 1 from the left of f of x, well, if we come from the left, our limit's 2. Our limit from the right of f of x, that's equal to 2. So our limit exists. We have a limit as x approaches 1 of f of x is equal to 2. And for point 3, that was our point 2, I didn't label it, f of x is equal to the limit as x approaches 1 of f of x. Therefore, we do have continuity. So this might seem pretty intuitive, but it is really important that we know where continuity happens. Let's do 2 more examples, then we'll kind of wrap this one up. If the function f is continuous, and if f of x is equal to x squared minus 4 over x plus 2, when x does not equal negative 2, then f of negative 2 equals what? Well, let's talk about this a little bit. F of x, I'm going to rewrite, is equal to x plus 2 times x minus 2 over x plus 2. All right, just factored that out. And I'll cancel some things out here. So therefore, f of x is equal to x minus 2. But of course, we know that x cannot equal a negative 2. So let's find what is f of negative 2. Well, f of negative 2 is going to be equal to negative 2 minus 2, which just equals negative 4. All right. So what does that tell us? That tells us that f of x has a removable discontinuity at x equals negative 2. So let's write that down. F of x has a removable, that would be like our jump or our hole, discontinuity at x equals negative 2. Where is that hole at? The hole is at negative 2 comma negative 4. Because we found our limit when x approaches negative 2 of f of x is equal to negative 4, right? So, and you could graph that and kind of see that in action. I mean, if you graph it, you won't be able to see that exact hole spot, but you will kind of get the idea. finally, oh, I have two more actually, sorry. For what values of the constant c is the function g continuous over all the reals? All right, so we have g of x is equal to cx plus 1 when x is less than or equal to 3, and cx squared minus 1 when x is greater than 3. So we want to know, where is this going to be continuous for all of the real numbers? Well, all we want to do is find out what c is, and to do that, we're just going to substitute in 3. So we're going to have 3c, oops, not 3c, excuse me. Pause for one moment. Yes, sorry, I lost my train of thought. So in place of x, we're actually going to substitute in 3. So we're going to have c times 3 plus 1, and we actually want that to be equal to 9, or I'll put c9, I guess, right? Kind of weird way to write these, but c9 minus 1, and I got 9 because I squared 3 right there. So then I can solve. I'm going to get 6c is equal to 2, and c is equal to 1/3. So when c is equal to 1/3, all the values are continuous for g of x. Okay, finally I want to talk about this last problem. Given h of x is equal to negative 2x minus 5 when x is less than negative 2, 3 when x is equal to negative 2, and x cubed minus 6x plus 3 when x is greater than negative 2, for what values of x is h of x not continuous? Justify. Well, we're going to justify this by saying, well, first we're going to point out that f of negative 2 is equal to 3. We're just given that information, right? But our limit as x approaches negative 2 of f of x, that actually does not exist, right? And we can see that if we graph that, and I've kind of already graphed it, but I'll just give it to you right here. If we graph this, we're going to see that negative 2x minus 5, 1, 2, it's going to be down here, kind of go up forever. And x cubed minus 6x plus 3, that's going to be about here and kind of go out forever. And 1, 2, 3, I'll just put it right here. There's our middle point, right? So our limit does not exist because our limit from both directions is going somewhere else, and you could calculate that. You know, you put in a negative 2 here, so you're going to get what? Negative 4, right? That's negative 9, right? And here you would get 8 plus 12 plus 3 is going to be 23. So clearly those they're not equal to one another, right? So if our limit does not exist, then our final justification is that f of negative 2 does not equal the limit as x approaches negative 2 of f of x. Therefore, h of x is not continuous at x equals negative 2. And that's it. Hopefully that all makes sense to you, and I'm looking forward to our next lesson. Thanks.